What do these different scenes have in common? These cars in busy traffic. This band playing music. These waves crashing on the beach. This dog barking. This fish finder. And this crowd of people. They're all producing sound waves. During the next few minutes, we're going to explore some of the different characteristics of sound and see how sound affects our daily lives. Have you ever been in traffic behind a car with music playing so loud that you can feel the vibrations? Ever noticed what happens when you hit a drum? Or hammer a nail? All these activities produce vibrations. Sound is the result of the vibration of matter. Most of the sounds we hear travel through air. But sound can also travel through liquids or solids. For example, put your ear against a door and have someone scratch the door. You can hear the scratching through the door. This demonstrates sound traveling through a solid. You decide. Can you hear music on the moon? No. Sound requires a medium, such as a solid, liquid, or gas through which to travel. On the moon or in space, there is little or no atmosphere, and thus no medium through which to carry sound. We've learned that vibrations produce sound, and that sound must travel through a medium. But how is sound transmitted? Sound is a form of energy and is transmitted in the form of waves. Sound waves are also called longitudinal waves. In longitudinal waves, molecules move in a direction that is parallel to the direction of the wave. This slinky demonstrates the movement of longitudinal waves. The area where the rings of the slinky are pushed together or compressed are called compression areas. And the areas where the rings of the slinky are spread apart are called rarefaction areas. The distance between two consecutive compressions or between two consecutive rarefactions is the wavelength. You decide. Do thunder and lightning occur at the same time? That's right. Thunder and lightning do occur at the same time. Even though we see the flash of light before we hear the roar of thunder, they originate at nearly the same time. This is because light travels faster than sound. In fact, you can estimate how far away a storm is by calculating how long it takes to hear the thunder after you see the lightning. There's about a 3-second delay for each kilometer between flash and thunder, or about a 5-second delay per mile. Light travels over 800,000 times faster than sound. Now, let's take a look at some of the factors that influence the speed of sound. Listen to this band play. The sounds produced by each instrument reach our ears at the same speed. This is because the sound waves from each instrument are traveling at the same speed. The speed at which sound waves travel is dependent upon the medium through which they are traveling, not the source of the sound. Sound waves travel faster in warm air than they do in cold air. This is because molecules move faster at higher temperatures. For example, on a winter day when the temperature is 0 degrees Celsius, sound travels at about 331 meters per second. On a summer day when the temperature is 25 degrees Celsius, sound travels at about 346 meters per second. That's quite a bit faster. Temperature, however, is not the only factor that affects the speed of sound. While most of the sounds we hear travel through the air, sound can also travel through other mediums, such as solids. You decide. Through which medium does sound travel faster? Solid, liquid, or gas? Sound travels fastest through solids. For example, sound can travel quite quickly through the ground. Generally speaking, sound travels faster through solids than through liquids, and slowest through gases. Sound waves travel fastest in solids because solids have more elasticity. In matter with high elasticity, particles travel quickly back to their original positions after being distributed. Liquids and gases are less elastic, making it more difficult for sound to travel through them. Therefore, sound travels more slowly through these mediums. When considering the speed of sound in matter of the same medium, density can play a big role. For example, in solids, sound generally travels slower in denser metals, such as lead, than it does in less dense materials, such as aluminum. This is because lead is less elastic than aluminum. We just explained why sound travels at different speeds, but why does the loudness of sound vary? Such as the difference between this loud music and this flowing stream. The different levels of sound we hear depend upon the amount of energy in the sound wave. For example, a louder sound is produced when a door is slammed hard than when a door is closed gently. The harder this baseball player swings his bat, the louder the sound of the crack when he hits the ball. The intensity of sound, or loudness, is measured in units called decibels. The sound level of a chainsaw is 90 to 110 decibels, whereas the sound of falling leaves is around 10 decibels. Sounds that are greater than 120 decibels can cause ear damage and permanent hearing loss, which is why this worker is wearing ear protection. The frequency of a sound wave can also cause sounds to differ from one another. For example, the sound produced by this sheep is different than the sound produced by this gull. These animals make sounds that have different tones. The difference in tone is due to something called pitch. Pitch can be illustrated by listening to the different octaves on this piano. This key has a high pitch, and this key has a low pitch. Pitch depends upon the frequency of a sound wave. Remember that frequency is the number of waves that pass a point in a given time. Sound waves with a high pitch, like this siren, have a high frequency. And sounds with a low pitch, like thunder, have a low frequency. Frequency is measured in units called hertz, which are the number of vibrations per second. 1 hertz equals 1 wave per second. On average, the human ear is capable of detecting sounds with frequencies between 20 hertz and 20,000 hertz. Some animals, such as dogs, can detect sounds above the human hearing range of 20,000 hertz. Sounds above 20,000 hertz are called ultrasonic sounds. We use ultrasonic sound waves in a system called sound navigation ranging, or sonar. This boat uses sonar to detect the depth of the ocean floor illustrated on this display screen. Sonar can be used to locate fish in a lake with this fish finder. Sound waves with frequencies below the human hearing range of 20 Hz are called infrasonic waves. We produce infrasonic waves. For example, when you swing your arms back and forth, a low-frequency sound is produced, but your ears cannot hear the sound. We've discussed how the frequencies of waves change the pitch of a sound. Now, let's take a look at what happens when the frequency and pitch change. You decide. What happens to the sound of a train as it passes by you? As the train approaches, the frequency of the sound increases and then decreases as it moves away. Notice how the pitch of this car horn changes as it passes by. As it approaches, the pitch and frequency increase. But when it goes by, the pitch and frequency decrease. This is the Doppler effect. The Doppler effect is defined as a change in the frequency and pitch of a sound that is caused by movement in the source of the sound, or the listener. Compare the sound of these fingernails on this chalkboard to the sound of this music. Which would you say is a more pleasing sound? The quality of sound, or timbre, depends upon the blending of different pitches in different frequencies of sound waves. Music has a pleasing quality, unlike the sound of this construction equipment. We refer to sounds that do not have a pleasing quality as noise. Noise pollution occurs when there are so many unpleasant sounds that it becomes stressful to us. Sound quality depends on the interactions of sound waves. Sound waves can interact in many different ways. You decide. What allows you to hear a conversation in another room, even though you can't see the people? The bending of sound waves around an object is called diffraction. For example, you can hear a car horn around the corner of this building. Sound waves can also experience refraction. When a wave travels into a medium of a different temperature or density, the wave changes direction. This is called refraction. For example, when sound waves called seismic waves travel through materials in the earth that have different densities, the waves bend or refract. Another interaction of sound waves that affect the sounds we hear is called interference. There are two types of sound interference, destructive and constructive. In destructive interference, the compression of one wave encounters the rarefaction of another wave, and they cancel each other. In destructive interference, the intensity of the sound is decreased. In constructive interference, the compression of one wave overlaps or combines with the compression of a second wave. The result of constructive interference is an increase in sound intensity. During the past few minutes, we've taken a look at the many different characteristics of sound. We've discussed the speed of sound and some of the factors that affect the speed of sound, including temperature, elasticity, and density of the medium through which sound travels. We also explored characteristics of sounds with different loudness. We studied pitch and frequency and explored their roles in the Doppler effect. Finally, we explored some of the different interactions of sound. So, the next time you play an instrument, hear a loud noise, or listen to some music, think about some of the different characteristics of sound. You might just think about sound a little differently. Fill in the correct word when you hear this tone. Good luck, and let's get started. Number 1. The intensity of sound, or loudness, is measured in units called Number 2. Sound waves with frequencies greater than 20,000 hertz are called Number 3. When movement changes the frequency and pitch of a sound, you experience Number 4. Occurs when too many unpleasant sounds put too much stress on the human ear. Number 5. Destructive interference causes sound intensity to Number 6. The term used to describe waves that bend around objects is called Number 7. Sound travels on warmer days than on cooler days. Number 8. Is a result of a vibration of matter. Number 9. Sound waves travel than light waves. And number 10. In a longitudinal wave, sound waves move to the direction of a wave.